Okay, hello everyone, and welcome to today's lecture. I'm assuming everyone can see my slides and can hear me clearly. Uh, if not, let me know. So, last time we were talking about the OS structure at a very high level. Today we are going to start the next module of our course, which is about processes. So processes are basically a fundamental concept in operating system because this is the way, this is the concept which allows you to understand how an operating system manages the execution of your code or your applications. So uh, today we are going to identify the memory layout of a process and also understand that how processes are represented in operating system and how they are scheduled for their execution. Also, after covering the setup slide, you should be able to describe the process creation using appropriate system calls. Uh, Let me just quickly make a correction here. Yeah, okay. And the topics we are going to cover are the process concept itself, how we schedule the processes, and operations on processes. We will today only cover the creation of a process, and then in upcoming lecture we also talk about other operations on a process, for example, process termination. So the course objective two will be covered in these slides, which is again partially understanding the execution of processes. So what is a process? So we know that an operating system, when we are running an operating system, it executes a variety of programs, and those programs they run as a process. So what the process itself exactly is? So process is actually a program in execution. So basically, it means that a process is a is a process is basically an active form of a program. When you load a program from your disk into the memory, so once loaded, it we can treat it as a process. Why? Because once loaded, it starts claiming resources. For example, the memory space, right? A process is process execution. It must progress in sequential fashion, which means that there is no parallel execution of instructions of a single process. But this is true only for single-threaded processes. So if we are assuming that we have a single-threaded process, then the execution of the process it will progress in sequential fashion, which basically mean that instructions of the program they will be executed one after the other. But this is not then true if we consider the multi-threaded process. But for now, we are considering or we are talking about single-threaded processes. So program is a passive entity, as I said earlier, which is just like a file which is stored on your disk, for example, as an executable file or ELF format. And when you load it or when you move it from disk into the memory, then it becomes active because then it starts claiming the resources, for example, the memory. It is possible that you have one program, but then that particular program is running several processes. For example, you can consider multiple user executing the same program, or for example, the same user running multiple copies of the same program. For example, when you are running your web browser and you are opening multiple tabs or you are opening multiple windows, so you have same program, but then there are multiple processes which are generated by the same program. So how the layout of a process when it is like when a program is moved into the memory and then it becomes a process, then how the layout of that process looks like in memory. So like what are the different segments within the memory which is occupied the process. So its layout consists of multiple parts. The program code, which is also known as it is also known as the text section, and basically it contains the code of your process, the code which is executed by the process, right? The current activity of your process is tracked by program counters and other processor registers. The program counter, it basically tells you what next instruction is going to be executed in the instruction sequence of your process. And other processor registers, they are used basically to hold the data which is operated on by the instructions of process. Stack, let me just select the pointer. So this is where this is just a section of the memory or a part of the memory where your program is loaded. But the memory occupied by your process you can then further divide it into it is further divided into several sections. One of those section is text section, which basically holds the code of your process. Then and as I said, the program counter actually indicates that which instruction is this in this code section is will be executed next. Stack, it is responsible for holding your temporary data. For example, let's say in your application, if you are making some function calls and you are making passing parameters to those function, so then those parameters, they will be stored in stack section of the memory which is occupied by your process. Similarly, return address and local variables, they are also stored in the stack section. Data section, it contains the global variables which are like defined in your program of your process, code of your process. And heap, it contains the memory which is dynamically allocated during the runtime. So if you see in the figure that heap and the stack, they are dynamic. That's why we have these arrows to show that they can grow and shrink according to the like requirement. For example, when you make a function call, so uh, then a function frame is created, something which is named as function frame is created on the stack. And when you are done with the execution of the function, then that function frame is removed. Similarly, so when the function frame is created, it's mean your stack is growing, and when it is removed from the stack, then size of your stack decreases. Similarly, when you dynamically allocate the memory, for example, if you have you used alloc or malloc functions in C programs. So what happens that your memory allocator of the operating system, it actually allocates memory to your program from the heap section. So the heap size increases. But when you use the free function in your C call, in your C code, for example, the size of the heap reduces because that memory is set free, which was earlier allocated by using the allocate function. So since stack and heap, uh, they grow towards each other, it is the responsibility of the operating system to make sure that they do not overlap. So heap doesn't grow into the stack and stack doesn't grow into heap. Otherwise, they will corrupt each other. So here is an example which shows that how for example, let's say you have this program. So when you run it, so when you load it in memory, so it becomes a process, right? So when it becomes a process, then different parts of the program are loaded into the different uh, section of the memory which is allocated for the process. So let's have a look how these different parts of the program map into the different memory sections. So the global variable, you can divide them into two like different categories, those which are uninitialized and those which are initialized. So that's why your data section here is divided into two subsections. One, initialized data and uninitialized. So X, which is uninitialized, goes to this uninitialized data section, and Y is equal to 15. It is also global variable, but it is initialized, so it goes to the initialized data section. Then the parameters for your functions, for example, even the parameters for your main function, they are they are allocated on the stack here, right? And stack then goes downward, which means that if you have any more parameters or any local variables, they will be placed at this position, and then stack will keep growing downward here, right? For example, here you have values and I, they will also go to the stack because they are local variables. And when you are dynamically allocating the memory, for example, by using the function malloc, a library function, a C library function. So this will result in allocation of the memory, and from where that memory will be allocated, it will be allocated from heap section, right? And then these local variables, for example, we have already initialized it here, so it is residing on the stack, and there is nothing other data in this core in this file. So all the data which we have in this file is already covered, and the whole of this program itself resides in this text section. Okay, any questions? Okay. So in Linux, you have this command size, which you can use actually to find size of the different sections of your executable file. For example, in my case, I had an executable file named stmm tiled matrix multiplication. So when I run the size command on this file, this executable file, so it shows me the information about different section of this file. For example, it tells me that text section is 3352 bytes in size, and then it tells me that data section is that takes total of 588 bytes, and BSS, which basically stands for block started by symbol, it is and just another form of like the data initialized data. So it tells me that it takes only 4 bytes, and this last column gives me the total size of my memory occupied by my process, so which is like 3944 bytes. Okay, so we said that process is basically a program which you have loaded from the disk into the memory. So, but then once you have loaded it, it doesn't mean that it is ready to run and you can directly start. You can directly allocate CPU to your process. So why? Because there are other processes which are also residing in the memory, and they also need to run on the processor or on the CPU. So what we do is that what we assign different states to a given process, and then only those processes which are in ready state, they are actually allocated the CPU, right? So let's first talk about the states of the processes. So as a process executes, it changes state. Well, actually, from the time point when a program is loaded into the memory, at that time point, it is assigned a state. So the initial state is new, which is the process is being created, and then when you load in the memory, definitely it is being created, and then it is given the state of new. A process is in a running state when its instructions are being executed. So actually, which means that it is occupying the CPU currently, right? A process, it can be in a waiting state, and this will happen at this state will be the state of a process when it is waiting for some event to occur. For example, let's say your process makes a system call or an IO call or any kind of event for which it needs to wait. So then what happens is that it is kicked out of the CPU and it is no more in running state, and we assign it the state of waiting. Ready, ready is a process that is not yet assigned uh, the CPU, and that is not yet waiting for any IO event to be completed. So it is ready to run, but it is not yet assigned the CPU. And the last state is when the process has finished its execution. So we name that state as the terminated state. So here we have the state diagram and transitions about different states. So initially you create a process. So at the time when you create, it is assigned the state of new, and then from the new state it is admitted into the ready state, but it is not immediately allocated the CPU. It waits for its turn. Then scheduler decide. For example, it can be possible that more than one processes are in the ready state at a time. Then it is the job of the scheduler, and scheduler is part of an operating system. So job of the scheduler is to decide or to pick which of these candidates should be allowed to run on the CPU. So scheduler dispatches a ready process, and when it does so, that ready process becomes starts running on the CPU, and which basically mean that it transitions to the running state. So when a process is in running state, then one of the three things will happen. one, either it will eventually complete its execution and exit and call the exit call, system call, at which point its state will change to terminated. The other thing that can possibly happen is that when the process is running, it is interrupted. Maybe there is an interrupt, for example, by some IO device, and the processor needs to take care of that interrupt. So what it will do is that it will kick out that process, and it will start executing the interrupt handling routine, or ISR, or interrupt service routine, right? So if that is the case, then that running process will be like when interrupt happen, it will move to the ready state and then again wait for the scheduler to dispatch it to the CPU. The other thing that can happen is when a process is in a running state can happen is like that process which is in a running state requests an IO service or input or output service. So if that happens, then the process basically means that it is waiting for the IO operation to complete, in which case the scheduler will again kick it out from the CPU and put it in the waiting state, and then it will stay in the waiting state as long as that IO or event for which the process waiting is not completed. Once completed, then it is again moved to the ready state, and then it will again wait for the scheduler to dispatch it to the CPU. So this is how these are like different states of the process of a process and how the transitions happen among them. Any questions at this point? Okay, before I continue, it just come to my mind. I want to share it with you. The project one module is not released, and actually I made an announcement. And why it is not released? Because this project one module is supposed to be about processes, but we are starting the topic of processes today. So it is not, fair or doesn't make sense to release before we have covered the topic. That's why it is delayed. Now it can potentially affect our schedule. So I will try to move the due dates of all the projects and their modules. I will try to push them down so that we can still have four projects, but we can complete them before the end of the semester, hopefully. Okay, so uh, okay, so we said that when a process is created, it can be once it is created, it can be in any of these three states during its lifetime. So, for example, when we said that a process is, for example, is running and then an interrupt happens and the CPU and the process is kicked out of the CPU, and then in at some future time it will be then brought back into the brought back to the CPU, which means it will be again assigned the CPU for execution. But then we need to take care of some things when this kind of situation happens. Like, for example, when the process is interrupted, we need to know at what point it was interrupted, right? And so that in future, when we allow it to run again, it should start executing from the same point, right? And also we need to keep track of like which process was interrupted, which basically means we need to know, we need to have a way to differentiate between different processes or to identify them, right? Or for example, let's say a process was running and an interrupt happened and the process was accessing a file at the time point when it was interrupted. A file was open, right? And the interrupt happened. Now, when in the future it is again allowed to run, we should make that file available to the process again in open state so that it can start continuing. For example, if it was reading, so it can start reading the file at the same point where it left, where it was interrupted, right? So it means that we need to maintain uh, a certain set of information regarding each process. For example, what is its ID? For example, when it was interrupted at what point? For example, if at the time of interruption, were there any files made available to the process and other information as well, right? So what we do is that we use a construct which is known as process control block to hold all the information associated with each process so that we can use that information whenever we need to whenever we allow a process to run, whenever a scheduler actually allows a process to run, right? So scheduler uses that information. So So that information is placed in process control block, which is also sometimes known as task control block, but these are two different names of the same thing. Okay. So uh, what is the information which is part of the process control block? You can see the figure here on the right side. So it is not complete, but the major major items which are part of the process control block are listed here. So most important of that is the process state, which actually tells us that process is in which state. Is it in running state or waiting state, or is it terminated or new, whatever. Okay. Uh, then another information which is saved in the process control block is program counter, which tells us the location of the instruction to next execute. For example, if a process is interrupted, so in the future when it is so we need to save its program counter. Where do we save it? We put it's the value of its program counter in this structure, and then save the structure in the memory. So when in future we need to allow that process again to run, we can read the value of its program counter from the PCB, and then we can allow then the process can start executing from the same point. Also, we need to store not only program counter but also other CPU registers, because the process which is running it may be using it may be holding some temporary data in the register file, right? So we need to store values of all those registers in the program counter sorry, in the process control block. And other CPU scheduling information. For example, if we are using priority based scheduling, then what priority was assigned to that process, and if that process was at the time of, like, let's say when it was interrupted, or when it was moved out of the running state at that time, which priority queue, which scheduling queue it was belonging to. So, or if it is using any queues, for example, so what are the pointers of those queues? Then also, what memory was allocated to that process, so that we can use that memory when we again run that process. Uh, okay, so uh, let me go back to go to OneNote, and yeah, let me just open new workbook or new file. Yeah. So, so let's say that we have a process, let's say process A, and it was in running state. So basically, it's mean that it was occupying the CPU, right? And let's say it has some instructions, and it was at this point, right? Let's say PC counter is, I'm just making up some number 10, right? And then an interrupt happens. So when interrupt happens, so this process is moved from running state to, let's say, ready state, but it is not yet scheduled. So now it will be like waiting for the scheduler to dispatch it again to the CPU, right? So, but before this happens, that before we move the process from a running state to the ready state, so let's say we have this process control block for process A. So here we save the process ID. Let's say the ID of this was X. So we save here. So this is actually in memory. So this thing, process control block, is in memory, right? So we save the ID here, and then not only that, we also save the program counter. So let's say we save here program counter is equal to 10, and when this execution was happening, So if I convert, let's say, into lower level assembly language, then let's say it was using some registers, and at that time register 1 was like so holding the value of 7, and register 8 was holding value of 20, and some other registers which are needed for the execution of this correct execution of this process. So I will also store the value of all those registers here in memory, right? And if whatever priority this process has, that priority will also be saved. So, and then doing this, then it will be moved to the state will be changed to the ready state, right? So this PCB is actually maintained by operating system, and it is stored in the memory. So all information which operating system needs to successfully run a process, that information is part of the process control block. Uh, so a question becomes that can a user process access process control block of itself or other processes, for example, if that process is written in C and running in operating system of Linux. So what is your answer to this? Anyone who want to respond to this? Can a user process access process control block of itself or other processes?
I think it should be able to.
And what is your reasoning for that?
That it can block processes.
So that it what?
So that it can block processes is the question.
So that it can block the processes. Uh, no, actually, remember who's responsible. What is the purpose of PCB? The purpose of PCB is to provide all the information which is needed by an operating system to successfully run processes and schedule them, right? So
Mm.
let's say if I am a user process, and for example, if an interrupt happens and I am kicked out of the CPU, and now my state is changed from running to ready. Let's say I requested an IO operation, and I am waiting for that IO operation to complete. So my state changes from running to waiting. Now, if as a user process, I can access and modify the content of my PCB, my process control block, I can change my state from waiting to ready, right? While the fact will be that my I operation is still not completed. So I will be giving wrong information to the operating system that, oh, I am ready to run, while actually I am not. I'm still waiting for the I operation to complete. Or if I'm allowed to access the process control block of other processes, so what I can do is like, if a process is in running state or in ready state, let's say a process is in ready state, I can simply go and change its state value in its process control block from ready to waiting. And in that way, I can compromise the execution of other processes. So that's why, which is not what we want to do, right? So that's why user process is not allowed to change or access the content of the PCB, and PCB is actually a kernel level data structure. So it is a construct and a kernel level structure. So user level application or user level processes cannot access it, and they should not be able to access it. Okay. So far we have been assuming that our process, which we are in our discussion, we are assuming a process which has a single thread of execution. Uh, but let's consider that if we have a program or a process which consists of multiple threads, then uh, it means then we need multiple counters per process, because remember we have also discussed it in one of the previous lectures that program counter is used basically to track the sequence of execution, and a thread actually is a software abstraction of a sequence of execution. So if you have one thread, so if for each thread you need one program counter and one core, right? So if you have multiple threads, it means you have multiple locations from where you can execute the instructions. So you will need multiple program counters. So this is known as like having a process with multiple threads of control or multi-threaded process. But we will not cover them at this time point. But just keep in mind, like for example, if we have a single threaded process, so we need all the information needed information in the program in the sorry process control block. So if now we have multiple threads, so it's mean that when we in future, if a process is interrupted and in future we want to run it again, we also need to track the information related to multiple threads. Just like if we have a single threaded process, we are having the information for that single thread process. Now, if we have more than one thread, we need to have also per thread information. For example, each thread has its own program counter. So it's mean that this time in the process control block, we will have we will store values of more than one program counter. Any questions? Okay, so uh, let's have a look at how the processes are represented in Linux. So we said that our operating systems, they have some kind of data structure to store all the information, and that data structure is named as process control block. So in Linux, they have a structure which is named as task struct, which actually represents the process control block. So it holds all the needed information, and some of those information items are shown here. For example, the process ID, the state of the process, uh, how much time is allocated. If, for example, when this process will be in running state, then how much time will be given to that process to execute on the CPU. After that time, it will be interrupted or moved out of from running state to the ready state, right? And also, who is the parent of this process? Parent is basically parent of a process, the process who has created the process, right? So if process A creates process B, then A is the parent, B is the child, right? And other information is the list of children of that particular process, list of the open files, and address space of this process. So in Linux, what happens is that uh, each process will have its own task struct, which is equivalent of saying each process will have its own process control block, and then those task structs, they are actually linked with each other. So for example, let's say this is a list of the all the all the ready processes. So they are like uh, one node in the list points to the next node, and each node is a task struct. And then in Linux, you have a pointer which is known as current, and it actually points to the process, the task struct of the process which is currently running on your CPU or on your core, right? If you want to see the actual definition of this task struct in the source code of the Linux, you can go to this link, and you can check that it is to check its definition at this line number. So it has a large number of information items, but these are the some major ones which we need to know. Okay, so uh, process behavior, what do we mean by process behavior? By process behavior, we mean that uh, how the execution time of a process is spent in doing what activity. So the activities which a process can perform are either they can be IO bound activities or compute bound activities. So IO bound activities, they basically means that your if a process is IO bound, then it's mean that it spends more time doing the IO operation than the computation. For example, maybe if you have a process which is frequently reading from your keyboard, then it is IO bound process. On the other hand, if you have a process which is not frequently reading from your keyboard but doing some computation, let's say on a large array of data, then it is a computation bound process, a CPU bound process. Computation bound or CPU bound is same thing. So CPU bound process, it spends more time doing computation and it has very few long CPU bursts. So what is CPU burst? So CPU burst is the execution of the program in CPU between two IO requests. So like if you have here, these are the two IO requests on the edges, how much time you spend doing the computation between request 1 and request 2, right? So that is known as CPU burst. So IO bound processes, they have many short CPU bursts. Why? Because they have frequent IO requests, like one here, one here, one here. So the size of each CPU on average becomes smaller. On the other hand, CPU bound processes, they have very few but long CPU bursts because they don't request IO operations that much frequently. So we may have a short or long CPU burst. So process swapping, uh, it may be, you may be feeling that I'm talking about random things, but they are not random. Let me first cover this process behavior, like IO bound process, why I'm talking about IO bound processes as CPU bound process, and then we will use this information in the upcoming slides. So it is just like I first want to define these concepts and then use in the following slides. So process swapping. So process swapping is, so before talking about swapping, let's first talk about degree of multiprogramming, which is basically the number of processes which are currently in memory. So higher the degree, the higher the computation for resources, because larger the number of processes in memory, it's mean that you have larger number of processes which want to run on the CPU. So they will be like waiting for their turn. So there will be higher competition for resources. So process swapping is the situation where we remove a process from memory to reduce degree of multiprogramming. So like for example, if you have overcommitted the memory, or your memory size is not enough to support a given number of processes, so what you do is that you want to free up some memory, so you will move some processes out from the memory to the disk, which basically mean that you are making them, how to say, you are converting them back to the program form. But the additional thing is that you are going to store their state, uh, or all the related information which is needed, because maybe at the time point when you are moving them from the memory to the disk, before that time point maybe they have partially completed their execution, and now you are moving them to the disk, or you are swapping them out. So you need to store the state of those processes in the disk, so that in future when you load them again into the memory, then they start and they get their turn to run on the CPU, then they start executing from the same point. So swapping out is like just moving your process from memory to the disk and then storing its current state in the disk. And swapping in is when you move that process back into the memory and you restore its state from the disk. Okay, process scheduling. So first thing, now we have covered what is the meaning of IO bound processes and CPU bound processes, right? So the job of the process scheduling is to keep our CPU as much busy as possible, right? So we don't want to have end up in a situation where all of our processes are heavily CPU bound. Because if all of them are heavily CPU bound, then what will happen? That there will be like too much competition for the CPU resource. On the other side, on the other extreme, if we have all of our processes are heavily IO bound, it's mean there will be very high competition for IO resources, and our CPU will be idle for most of the time, right? So we want to have ideally a situation where we have a good mix of both IO bound processes and CPU bound processes. Because why? Because remember, CPU bound is one which is executing most of time on the CPU, and IO bound is one which is executing most of it, spending most of its execution time doing IO. So if we have like let's say a set of processes where 50% of them are CPU bound and 50% of them are IO bound, then what we can do is like we can keep both our CPU and our IO devices busy, right? So process scheduler, it is a component in your operating system, and its job is to select among the available processes for next execution on your CPU core. And when we say among available processes, it's mean those processes which are in the ready state. Keep in mind that state diagram for the processes where each process can be in any one of those states. Like it will be new, ready, wait, new, ready, waiting, running, or terminated, right? But process scheduler will select only those from those which are in the ready state. So what is the goal of process scheduler? To maximize the CPU use by quickly switching processes onto CPU core. Why we want to quickly switch the CPU cores, processes on the CPU core? Because as I said, it can for two reasons, which actually we have covered in one of the previous slide. For two reasons. One, that it is possible that a process which is running on the CPU core, it requests an IO and now it is waiting. So if we don't switch it out, then it is wasting the resource, the CPU resource, right? And the second is like second situation is like even if a process doesn't make a request for IO for the IO device, or it is not for waiting for any event, even in that case we still want to switch it frequently. Why? Because we don't want to end up in a situation where a user feels or experiences like his or her process is not making any progress. Why? Because maybe his or her process is not getting the turn because another process, let's say process A, is all the time running and is not waiting for any event, and hence is never kicked out. So the first situation is like multi-programming, and second is time sharing. And time sharing is same as multitasking. So last time a student asked me what is the difference between multitasking and multi-sharing. So sorry, multitasking and multi-programming. So multitasking is same thing which we have covered in the slide. It is just a different name. So we talked about time sharing. So what we basically do is that we allocate a time chunk to each process, and when that time chunk is expired we kick it out even if it is not waiting for any event to happen and it is doing the compute. Still we kick it out, and we then allocate the CPU for to another other process for this given amount of time or for a time chunk. So this is known as time sharing or multitasking. Okay. uh, The job of the scheduler is also to maintain the scheduling queues of processes. What are those scheduling queues? We will have a look at them in a figure which we have in upcoming slide. So actually, during its lifetime, a process it can migrate among various queues. For example, it can be in a ready queue. A process can be in a ready queue. So ready queue is actually a set of all processes residing in main memory. They are ready and waiting to execute. So here this term is a bit confusing. The ready to execute mean that they are ready, but they are yet not allocated the CPU. They are not waiting for any IO. They are just waiting for their turn to have the CPU. Okay. Wait queues. It is set up processes which are waiting for an event. So they are not waiting for their turn to get the CPU. They are actually waiting for an event to complete. For example, an IO operation. So schedulers, there are two kind of schedulers. One is short-term scheduler, which is invoked frequently, for example, in milliseconds, and it must be fast. So this is the scheduler which is actually implementing your time sharing or multitasking, right? And the other scheduler is long-term scheduler, which is invoked very frequently, and it may be slow. So this scheduler is basically invoked for swapping your processes, for example, swapping out to the disk. And it is used to control the degree of multiprogramming. Remember we said degree of multiprogramming basically mean that how many distinct processes are actually active are loaded in the memory. And if you load too much processes, it can happen that you end up in a situation where you are short in the memory, or low, you are running low on the memory, so you want to free up the memory. So this is the job of the long-term scheduler, to keep track of like memory usage. And if the system is running on low memory, it will swap out some of the processes to the disk. So what kind of processes we can have in memory? As I said, we ideally want to have a good mix of IO bound and CPU bound processes. Why? I already gave you the reason for that. Anyone who want to share that reason or reiterate that reason? Why we want to have like a good mix of IO bound and CPU bound processes? Like for example, why it is not, it is a bad idea to have 80% of the processes as CPU bound processes and 20% of those processes as IO bound processes.
To maintain efficiency, because if it's CPU bound, it's all sitting on the CPU, but we aren't getting any input output work done, or vice versa. If it's all IO bound, then we're working on a lot of IO when a lot of CPU is just kind of sitting there being unused.
Yeah, that's correct. Actually, to avoid the resource wastage, or in other words, to maximize the resource utilization, right? We don't want our IO resources to be wasted or CPU resources to be wasted. Yeah, thank you. So how the queues they are maintained, or how the processes which belong to a queue, how they are maintained or managed, right? So for example, let's have a look at the ready queue. So let's say you have two processes, process 7 and process 2, both are in the ready state, and they are actually waiting for their turn to be assigned the CPU, which basically means that currently some other process is running on the CPU, and these two are in the ready state, but they are not yet allocated the CPU. So then your operating system will maintain a list of their process control blocks, where it will have a header and a tail. So it will head will basically point to the first process control block in the list, ready list, and tail will point to the last process control block in the list. And then each process control block will actually point to the next process control block in the list, just like here. And if there are other, they will be connected at the end of the list. But it doesn't mean that when a process is picked from this list for running on the CPU, it doesn't mean that it is always the process on the head side. It can be like you can use different criteria or different scheduling algorithms to pick one of these candidates. So all of the processes in this list are candidate, but then what is the criteria to pick a candidate to run on the CPU? For that, you can use different algorithms. So again, here we have an example of wait queue, where you have again header and tail, or head pointer and the tail pointer. So all the processes which are waiting for some kind of event, they are linked together in the form of a linked list. Head points to the first element in the list of the process control blocks, and the tail points to the last one. Okay, so uh, how the process scheduling works. So this is like graphical depiction of scheduling, or how things work when a process moves from one state to the other state. So when a process is created initially, it enters the ready queue, and then ready queue is like implemented as we have seen here. Uh, and then it is waiting for its turns to be assigned the CPU. Once it is assigned CPU, it is in the running state here, right? It is in the running state, and once running on the CPU again, if it completes, then the state changes to terminated. And if not, then either it will be that like different things can happen. Either that process will request an IO. In that case, it will be like moved from running state to the wait state, but then it will also be put in the when it requests the IO, it will put in the IO wait queue, right? And here we have seen the wait queue, like you can assume that this is an IO wait queue, like, right? Other thing is like when another situation when it is moved out of the CPU is that you are doing the time sharing and the time slice which you have had allocated to the process is expired. Let's say you had said, okay, I will run it for 1 second, and 1 second is expired. So after that, you will move it again out of the CPU and its states become again ready. So this is just an event which causes the process to move from the ready state to another state. So it will go again to the ready state and will be appended in the ready queue and wait for its turn to be given the CPU again. Another thing can be which can happen is that a process creates a child process, and then after creating the child process, it waits for the child process to complete its execution. So again, it's mean that it is waiting for a queue. So it will be entered again in a it will be again put in a queue. And when that child will terminate, then it will again be placed back into the ready queue. And here again, when I forgot to explain this part. So when IO process completes, that process will be moved from the wait queue to the ready queue. Another thing that can happen is that is the interrupt. So if an interrupt arrives, your process will be moved from the ready state to the wait state, and it will be placed in the wait queue for that particular kind of interrupt. And when that interrupt actually is serviced, actually it should not be because it should be interrupt serviced, right? So when that interrupt is serviced, then the process can be moved back into the ready queue. Okay, so when you execute the processes, let's say you if you have a single core and you are executing two processes on that single core, it's mean you are doing the time sharing, right? So when you are doing the time sharing, uh, let me let me quickly try to draw a figure to explain. So let's say you have this core, I'm naming it as core 0, and you have two processes which are sharing this core, process A and process B. But at a given time, you can run only one of these processes on the core, right? Let's say that first you allocate core 0 to process A and it is running in this time period, right? So it is running in this time period. So if when it is running, then process B, it must be in the wait state. So it must be, let's say it is not waiting for any event, but it is in the ready queue, right? And then let's say this is the time period or the time slice. Let's say I am just putting some number, 1 second. So after 1 second, what happens is that core is allocated to process B. So let's say next 1 second, process B executes and your process A moves from running to ready state, right? However, this transition, which we are showing here, this transition, where like you move the process A out and you bring in the process A and it starts running. So it doesn't start running immediately, right? Why? Because you need to first store the information of the process A which you need for successfully running the process A again in future, right? Because now it will go to the ready queue, and once it is again dispatched from ready queue and becomes and its state is changed to the to running, then you need to have some information. For example, let's say this is your code of the process, right? And at this point it was interrupted. So next time when you restore it, you need to know that this was the point of interruption. This instruction it was executing, it has executed this instruction, and the next instruction that is to be executed is this one, right? How you know this one? By putting the program counter where in its PCB, which basically means that you need to store its PCB in the memory. So you need to store the PCB of process A in memory, right? And not only that, before running this process B, you need to store its piece. You need to load all the information from PCB of the process B into corresponding registers. For example, in program counter, or if some other registers were being stored, whatever their value was, load that value into those registers like R1, R2, or whatever, right? Or other information like, for example, what files were open for this process B, or what memory was allocated for this process B, or what IO devices were assigned to this process B, and so on, right? So this step of storing the process control block of process A in the memory and restoring the values from process control block of process B into corresponding registers, it takes time. It doesn't happen in zero time, right? So, and this process, first thing, this process of like storing the PCB of process A and reloading the values from PCB of process B is known as context switch. Okay, so let me go back to the slides. So context of a process is so what the context itself is. So context of a process is the necessary information which you need to run that process successfully in future. And where is that information stored? That information is stored in PCB. So in other words, we can say that PCB is the context of a process, right? And it include information like, as I said, program counter, process centric registers, and memory management information, and so on, right? So when a CPU switches to another process, the system must save the state of the old process and load the saved state for the new process via a context switch. Just like I explained in the drawing. So this context switch time is pure overhead. Why? Because our CPU is not doing any useful work. Any useful work from the perspective of our user processes, the processes uh, uh, which are being switched, from the perspective of those processes, we are wasting the time, right? And this overhead, the amount of this overhead or the time needed for performing the context switch, it actually depends upon on multiple factors. For example, if more complex your OS and the PCB, then longer it will take for the context switch. For example, lesser information you are storing in the process control block, it will take less time to save the information in the memory and restore that information from the memory. Longer the size of the PCB, longer time it will take to do the context switch. Also, the time taken by this process by this context switching, it depends upon the hardware support. For example, some hardware they can provide multiple set of registers per CPU, and hence it means that you can have multiple contexts loaded at once. I don't know whether this last statement makes sense to you or not. If not, let me explain. So let's say that we have a single core, let's say, okay, and it has let's say one program counter, and it has, let's say, 4 general purpose registers in a register file. So this is a register file, right? And now let's say the process A is running, right? So process A is running, and I'm just writing R for running. And then the time slice which was allocated to it is expired. So then its state moves from ready to let me write run, because both ready and run start with R. So then the state needs to be changed to ready, right? But before doing that, we need to put these registers. Let's say this is the minimum information we need to put in the PCB. So we need to put, let's say, the ID of the process, the PC, and values from these 4 register files, right? right? So now in the future, when you are sorry, not in future, when you are now going to put process B on the CPU, like you are moving it to the running state, then let me write here PCBA. So what you need to do is that you need to move this value, let's say I'm naming it as PC prime, into the PC. Similarly, you need to put the values of its registers, let's say I'm naming it as R1 prime, R2 prime, whatever their values are, put them in this register file. Now it takes time. Now, how can we how can we avoid that time? So here again, maybe internally we have only one execution engine or execution pipeline, right? But we want to we want to reduce the latency of doing this, like loading from PCB of process B and like storing the PCB of process A. So what we can do is that instead of restoring the values from PCB of process B into program counter and register file, we can say, okay, in the same core, and there is no this boundary, in the same core, I have another PC, right? And here I have another register file. So when I context switch and I say, okay, process A is going to ready state and process B will be moved to the running state. So I simply tell execution engine, okay, don't read the value from this PC, read the value from this PC here and from these register files. So at the time point in past when process B was context switched out, its values was not saved in the memory. They were held in these registers. And I simply need to change the pointer, like from execution engine or execution pipeline, from which PC it is going to use, right? But then it means that, okay, at a time, I can use this hardware optimization only when I am sharing the core between two processes. But what if I need to share the core among four processes? Then I have at most only two set of PC and register files. So it's mean I need to again fall back to the same approach of using process control block and saving them in memory and restoring them from memory on the control on every context switch. Okay, so this is what we are saying, that this time of the context switch is dependent on hardware support. So some hardware or some architectures, they provide multiple set of registers per CPU. So in such cases, if that is the case, then multiple contexts they are loaded at once. So both of them are available on chip, and then you simply need to just change the pointer from where your execution pipeline is going to read the values. So definitely this is like our simplified explanation of the idea, because as we said, process control block can have a lot of other information, not only program counter and other general purpose register values. But then, I mean, this is one approach which can be utilized. Okay, so we have not too much time left. Okay, let me cover this figure. Okay. So a context switch, it occurs when the CPU switches from one process to another. It is essentially the same thing which I have said. So you have two processes, P0 and P1. So let's say process P0 is executing and then some interrupt happens. So control goes to the operating system. It saves the state of the process 0 in PCB0 and then reloads the state from process PB1. And then after loading the state, it allows the process P1 to start executing, right? And when it is executing, let's say it makes some interrupt, a system call happens, and then we save the state of the process 1 in its PCB and load the state of the process 0 from PCB 0, and then it starts executing. So here this process is idle, waiting for its time. Here process P1 was idle in this time period and in this time period, right? So what is the total time from which is wasted from the perspective of the process? The time that is wasted from the perspective of the process is this one, right? These two red circles, because here process is not doing our core is not doing any useful work from the perspective of the processes. Yes, it is doing some useful work from the perspective of the operating system, but from the perspective of user processes, it is wasting. We are wasting the resources. Okay, let me stop here because you guys have a quiz. So please go ahead and start doing your test, your quiz. I'm here online until end of the lecture time.